Hi, welcome everybody. It's my real pleasure today to welcome our seminar speaker, Christian Claudel, who is going to talk about various topics related to transportation and water systems. So as a short introduction, Chris comes to us from the École Normale Supérieure in France, where he got 2 masters in plasma physics and applied physics. And after that joined Berkeley as a PhD student. He was a student from 2007 to 2010 in the electrical engineering department, where he received his PhD. Noteworthy and connected to this talk, he was awarded the Leon Chua Award for his contributions in nonlinear optimization and nonlinear systems, specific to the Hamilton-Jacobi equations that he tackled for his PhD. He joined the KAUST University in Saudi Arabia, King Abdullah University of Science and Technology in 2010, where he has been an assistant professor for 4 years now. And at KAUST, Chris was the first person to build KAUST's first UAV program, and we'll hear a little bit about this, as well as very interesting work on sensor networks. For those of you who have visited KAUST, it's quite amazing. Chris's sensors are all around campus, and they've done phenomenal things. And finally, so Chris is coming back to the US. He will be joining UT Austin in the spring in the civil engineering department. So please join me in welcoming Professor Chris Claudel.
Thank you very much for the introduction, Alex, and it's my great pleasure to be here giving this talk at the CITRIS Fall 2014 Seminar Series. My talk today will be heavily focused on systems, and I'm going to present something on wireless sensor networks for flash flood detection and traffic flow monitoring in cities. And this is really systems intensive. I think I've been driven to study systems ever since I was part of CITRIS as a PhD student. I really like the concept of trying to accelerate deployment of systems. So the issues that I want to tackle specifically are urban, energy, and water challenges. So in particular, you have to realize that most of the population nowadays lives in cities, more than 50% in fact. And you have numerous challenges when dealing with the operation of these future cities, because you have to guarantee the safety of users, and you also have to make these cities somehow more efficient. You want to improve the efficiency of the transportation network and the water network, as well as the power grid, for instance. So among these issues, I want to tackle these 2 specific sub-problems, which are transportation networks. How can we make them more efficient, more resilient? How can we improve the efficiency of transportation? And I want also to tackle flash flood disasters. This was really motivated by me being at KAUST, because shortly before I joined, there was a major catastrophic flood in the nearby city of Jeddah that killed 400 people. And the issue is that there is no real-time estimation and real-time information dealing with these floods currently, and you can see that for the floods that happened just recently in the Indian-Pakistan border, which killed almost 600 people. So in terms of traffic, traffic congestion is a huge societal burden. It costs us about 3 billion gallons of fuel. That's about 8 days of the daily consumption of fuel. In the US, it costs $800 per person. That's a lot of money. And you have many ways to address traffic congestion, but you have to realize that one of the easiest ways is to actually control the state of traffic, is to allocate people and to modify the way they travel on the transportation network. And in order to do efficient control, the issue is that you need efficient systems that will provide you highly accurate estimates of the traffic, as well as highly accurate forecasts. And we don't have this yet. So yet, if you try to implement traffic control, you will probably have an actuation that is worse than no control at all. In terms of the flooding, floods are the most common natural disaster in the world. More than half of the casualties are actually caused by floods. In the US, you can see these figures. They cause more casualties by far than all these natural disasters combined. And most of the casualties are actually caused by drowning. And people drown simply because they are not warned of the dangers of the flood. They don't get real-time information about what's happening. Sometimes they try to ford rivers in cars, but unfortunately they don't know the severity of the flood, and sometimes they don't even know at all that the flood is coming, which was the case in Jeddah. So now to address these two issues, my objective was to build a dedicated wireless sensor network that would monitor both phenomena at the same time. And this sensor network would leverage what we call Lagrangian sensing. Lagrangian is a fancy word for mobile sensing. So it's going to use, for the traffic components in particular, vehicles as sensors. And why we want to use vehicles? Because there is a small revolution happening in the transportation world. This is called V2I or V2V systems. Those are dedicated short-range communications between vehicles and infrastructure. And because this will be most probably mandated in the next few years, you will have potentially a lot of cars that will transmit data, and we want to leverage this data to have to solve the transportation estimation and forecast problem. So in terms of flash floods, we wanted to build sensors that detect flash floods. The issue is that if you just build a sensor that detects flash flood alone, you're not likely to get anybody investing in this technology. Why? Because even though flash floods kill lots of people, if you look at the risk of flash flood in a given region, the occurrence of catastrophic flash floods is very rare. Typically, for instance, in Jeddah, it happens every 100 years. So because, for instance, it happened in 2009 in the city of Jeddah, there is no real incentive to equip the city with dedicated sensors that may last 10 or 15 years and that might be useless in the end. So you want to have sensors that are multi-purpose, and this was really a driving factor in our design. We wanted to build sensor systems that could detect, for instance, traffic and flash flood together, as well as the corresponding architectures. So this is the outline of my talk. I'm first going to tackle the privacy problem. So why privacy? This seems a bit odd, but to me privacy is the main factor that limits the adoption of vehicle to infrastructure technology. So I'm going to present first a framework that is actually extracted from a more general framework that is capable of predicting and estimating if privacy intrusions are possible given a dataset. I'm then going to talk about the privacy-preserving architectures that we have developed at KAUST, and I will then show the dual traffic and flash flood wireless sensor network system that we have designed and operated on campus. So if we want to tackle the privacy problem, we have to somehow integrate the effects of traffic flow model into traffic flow data to obtain the likelihood of intruding the privacy of users. And the model comes here in the form of the Lytle-Witham-Richard models, which is a very well-known model. I mean, it's based on this partial differential equation here that simply translates that vehicles don't appear or disappear on the highway. It's a conservation equation that is combined with this equation that says that there is a direct relationship between flow and density on highway. So it's not extremely accurate, but it's a very robust model, so which is why we are using this. And if you change a little bit the formulation, you can actually express this model not in function of the density of cars on the highway, but in terms of this function m here, which is essentially the integral of the density function. And this m function, which is known as the Moskowitz function, represents the label of vehicles on the highway. So the physical interpretation of this m function is that if you were on the highway, if you labeled vehicles here in increasing order, the value of the function m here would be the value of the label at which you are looking for the specific time that you are looking. And this m function here obeys an Hamilton-Jacobi PDE, which is why we are doing all this trick, because now we can leverage the properties of Hamilton-Jacobi equations. So before we go into the framework of the privacy estimation problem, I'd like to just show you how we are going to solve the Hamilton-Jacobi PDE and why it is so important to solve it this way. So if you are looking at the traffic flow model, as for instance LWR or Hamilton-Jacobi, you have many ways to solve these PDEs. For LWR, you can use, for instance, first-order schemes or refinements on these first-order schemes. You can use wavefront tracking, which is a more exotic method. For Hamilton-Jacobi, you can use Lax-Friedrich methods, for instance, which is first-order. You can use dynamic programming. And the method that we're going to tackle today is semi-analytical. Which means that it's going to be the minimum of explicit or some operation on explicitly computed functions. So I'm going to introduce this, and this actually way of computing solution is the basis of building the estimation framework that I'm going to present. So the framework that I'm going to present is very general. I'm going to do another talk on Friday for the ITS seminar, which is on traffic control, and it's leveraging essentially the same framework. So let me tell you how we are going to approach this. First, let's consider a boundary data function, C here, which is completely arbitrary, which is defined wherever you want it to be defined. And to define this function C, let's consider the space-time. So here you have time, here you have space. So space corresponds to the highway. And you have data. So you have data that is generated by a bunch of sensors. You have, for instance, boundary flow sensors that detect the flow on the boundaries. You have initial conditions if you have, for instance, density sensors that tell you the density. You can have also conditions that are imposed on the solution, inside the solution, which can be, for instance, data generated by cars. So you know that the label of the vehicle that is following this line is the label of the car that is generating the trajectory, so that should be constant. And you want to somehow impose all these things on the solution. So you want the solution to reflect all these constraints, to satisfy the initial boundary conditions, as well as these things. So when you want to compute the solution to this problem, you can apply the standard Laxop formula. So the Laxop formula for a given C function here, which can be defined on this domain, doesn't matter where it is defined. MC is the solution associated to this C function. It's the solution to a minimization problem. So it can be computed explicitly using, it can be computed, yes, explicitly using dynamic programming. So you can march a grid and compute forward to compute the values of MC everywhere on your grid. Instead of using this method to solve the problem, we're going to leverage the infmorphism property that can be seen directly from this equation that I just showed, from the Laxop formula. So to do this, let's assume that the boundary data C is the minimum of a bunch of functions, which we're going to call Cj's. And these functions here, they correspond to the decomposition that I'm talking about. So instead of looking at this C function that is defined here in red, I'm going to break this C function into a bunch of components here, Cj's. So you're going to have a C1, C2, C3 that are there. You're going to have up to C12. So here you have 12 components. Well, what the infmorphism property tells me is that if I want to compute the solution at any point of space and time, the solution is going to be the minimum of AMCJs, which are the partial solutions that I would obtain if I were solving the problem, each problem for C equal to Cj. So I would get a bunch of partial solutions. And the actual solution is the minimum of these partial solutions, which means that here in the present case, if I'm worrying only about C2, C3, C4, C8, and C10, I'm going to compute the partial solutions. So here MC8, MC10, MC4, MC2, MC3. And if I want to compute the solution associated to all these things together, I just have to take the minimum of these functions. So of course, if you look at this from a distance, it doesn't look like we are helping finding the solution, because now, okay, your solution is the minimum of a bunch of functions, but still these functions MCJ, I still have to compute them using the Laxop formula. Well, it turns out that if your function Cj's are linear, then the solutions MCJ can be explicitly computed. Because when you plug these functions back to the Laxop formula, the problem that you have to solve is a 1D convex optimization problem. So it's very easy to solve. And you can actually solve this explicitly for any, you can find an explicit formula for these MCJs. So you can get these explicit formulas, put them in MATLAB, and all you have to do essentially is take your problem, break it into linear pieces like this. And once you break everything into linear pieces, compute the solutions. And once you have computed the solution, you will get, once you have computed the solutions, you will get the function MC of Tx. So you just have to break everything in linear pieces and apply the property that the solutions of MCJs can be explicitly computed in this case. Now, the advantages of this formulation are twofold. First, it's very fast compared to standard schemes. You are actually you are having much better performance than typical schemes, like for instance Godunov. And it also enables an exact derivation of the function that you want to solve, because now we have written that the solution was the minimum of explicitly computed functions. So we can compute these solutions explicitly, and the minimum won't bring any error. So you will have actually the exact solution to your problem. It can also integrate very easily mobile data, which is why we were interested in in this method. The only downside to this method is that if we are going to have an Hamiltonian that depends on space or time, then this method breaks down because it's based on the fact that we are having a constant Hamiltonian. So it's called homogeneous problems in the transportation community. So now let's build on this computational method for solving the equation to write down what our privacy analysis problem is and how to solve it. So what we consider now is a problem in which we have a bunch of data coming from sensors, a bunch of partial user trajectories. So we have a bunch of pieces generated by data. So this is generated by by users. So this is generated by a user, another user, and a third user here. And what we want to do is to try to re-identify users. So we want to say, okay, C10 was generated by a user, but maybe this C11 is actually generated by the same user, or maybe it's C12. So you have a bunch of people on the road, and you want to try to match people together to see if you can invade the privacy of users, if you can reconstruct the path of people, and that's essentially what we try to do here. So you have many methods to do this. You can either have methods based on a non-PDE based model, so you are going to have a model of users, you're going to take assumptions on how users behave and use that to try to identify people. What we tried to choose instead was a PDE based model. So in a PDE based model, you're going to leverage all the information that you have from your other sensors as well as the data that you have to try to, based on all this information that is available to you, re-identify what is the most likely location of your user. So you could think, okay, we have all these components here that come from our sensor data, so let's just take all these components, plug them into a C function, compute the solution explicitly, and that's it, we have our solutions. So based on our solutions, we'll be able to know what's happening because we can know the solution is computing the label of everybody everywhere. So you can check if the label of this is equal to this or this. The issue with that is, of course, that these CJ functions are not known. Why? Because you have two reasons. You have first things that are unmeasurable. For instance, the C10 function, it's imposing a label on some location. However, the car that transmits the data doesn't say, hey, I'm car number 55 and I'm transmitting my data. It has no idea of what is the label of cars around this car. So you don't know this. This is an unknown parameter. And you have a bunch of other unknown and unmeasurable parameters that are here. You also have parameters that are not known exactly. For instance, here, this boundary flow condition is going to tell you the flow is this value, but you know that your measurement value is not exact either. So you shouldn't impose the measurement value directly. You should impose a value that is within some bounds of what you have measured. So you have actually a bunch of unknowns, and you put all these unknown components into a decision variable, and you solve a gigantic optimization problem to try to reconstruct a trajectory of users. So I'm not going to go through this optimization problem explicitly, and this is going to be the focus of my talk on Friday. So you are welcome to join if you are interested in the approach. But you have a few main results. First, the constraints that are caused by the PDEs are mixed integer linear in the decision variable that you choose. So it's a good way of expressing things. Not perfect. I mean, it's not just linear, but it's mixed integer linear. You are going to have measurement constraints from your sensors, and these constraints are linear. And in the case of privacy analysis, your objective function is the difference of the label, so the absolute value of this difference, which is also linear in this decision variable, modulo slack variables, of course. So once you have all this, and here I just want to give you briefly the formulas that are corresponding to these model constraints. So the objective is, of course, not to go through these formulas, but just to see that these constraints are actually functions of both these explicit solution components that I described earlier, which are in red. They also depend on these boundary initial and internal condition data components that I talk about. So this is essentially your sensor data. This is the influence of the model on this sensor data. And you have a bunch of other constraints that are them mixed integer linear, which corresponds to continuity constraints of the solution. You want the solution to be continuous. That's a prerequisite. And these are the constraints that are in fact integer linear. So this is where the non-convexity arises. The rest is convex and linear. So now let's see the results of this framework. So we are going to do a test setup in which we're always going to consider one vehicle and two possible tracks that this vehicle can take. And all of this is, by the way, actual traffic data, and this was generated at UC Berkeley. This is the Mobile Century dataset that was generated in 2008. So it's actual traffic data of 8 hours, including sensor data from the PEMS system in California, as well as user-generated data from GPS cell phones. So if we consider this specific problem, we plug it into the framework that we talked about. And we want to estimate whether this corresponds to the same car as this or this. What we have to do is to solve an optimization problem in which we try to minimize the difference in label between this vehicle and this vehicle, subject to the constraints that you have measurement data and that you have a model. So subject to these constraints, you're going to have a mixed integer linear program, linear objective MIL constraints, and you're going to get here the scenario in which I try to adjust all the free variables as well as I can. And in this case, I know that there is a difference of 41 vehicles between both labels. So I know that for sure this cannot come from the same vehicle, because if they came from the same vehicle, I could arrange things, if the model is good, of course, I could arrange things in such a way that the minimum of the difference is 0, which is the case for the second track, for instance. So this second track, you have a minimum label difference of 0, which means that I arrange everything in such a way that now I know that they can possibly be the same car. And I know that here, in the best case, what I can put is a minimum separation of 41 vehicles in between these two components. So I know that this cannot be the same car. This is possibly the same car. Again, I have no guarantee. I just managed to put my free variables in such a way that they could be the same car, but I'm not sure. But because I have only two choices, I know that this is going to be the re-identification result. And in fact, in this present case, this was the case. Because we got label data from Mobile Century, we knew exactly which was the car that was generating which data. So we know that this data was generated by the same car as this data. So here we were very happy when we computed this, because we had an example that showed that actually the model was able to correctly predict that the most likely track was this instead of this. And if you look at just purely simple models that take a constant speed, you would assume that this is much more likely to happen. So we were happy to show that the model was able to predict this. However, it doesn't work perfectly, because when you now average this on a bunch of programs, you will realize that it doesn't perform better than simple naive identification, which is what I talked about. I mean, you take one track and you try to identify people, assuming that people get the same speed, essentially. So it doesn't perform significantly better than naive identification. Why? Because first, it's sensitive somehow to the model parameters, but not that much. LWR is still quite robust. The main reason is that the LWR model is very poor model of the propagation of cars in free flow. It's very simplistic. It assumes that in free flows, cars have all the same speeds. And of course, we know that people don't have the same speed in free flow. So you can exploit the difference of people setting different speeds, and you can actually try to identify based on this assumption, which is not encoded by the LWR model. So what we did to solve this was to train an artificial neural network, taking into account these features that we were computing based on the model, as well as other features which are, for instance, the distance to the predicted location, as well as the internal condition velocities. And when you train an artificial neural network based on these model outputs, you get actually much better identification performance. So we did this analysis averaging 5,000 problems that were all extracted from the Mobile Century data, so 8 hours of data, representing very various conditions of free flow, congestion, and stop and go waves and everything. And we found out that if you just use the naive re-identification model, so you just assume that the cars all have the same speed, and you try to match cars based on this assumption, you get 86% good results, which is fine. And in fact, this works well because in most of the cases you have free flow conditions, so you still have a bunch of possibilities for having good re-identification. Now, if you add another feature, which is the velocity of the internal condition, you get, of course, a better result in the artificial neural network, because now the artificial neural network understands that if your speed drops, you are likely to have congestion. So the classification of which one is the likely successor of a piece of data is not as obvious, and you can have a slightly better performance. So all this is, of course, on the validation dataset of the neural network. And if you now add an extra piece, which is the prediction of the model, so these two terms, these two features that are solution to the prime, are the relaxation terms, so it indicates how well the model fits the current situation, and the label difference, so that's the solution to the optimization prime. So if you put all these together, you're now having 94% re-identification performance. So you have a much better re-identification. So these sum not that much of an improvement. 86% was already good. 94% is, of course, better. But what you have to consider is that when you try to solve these re-identification problems, you try to find the distance after which you have 50% chance of having lost track of your user. Because each time you re-identify a user, you know that there is a probability for you being wrong. And if you just adopt this strategy, with 86% likelihood of finding the correct successor of a trajectory path, that means that after 4 re-identification primes, you are basically lost. You have 50% chance of being lost. With 94%, now you have to go through almost 10 steps before being lost. So you have actually a much better shot. So each % improvement is actually a huge improvement on the re-identification of these models. And which was a nice feature also is that we tried to modify slightly the parameters we modified by 5% all the parameters of the LWR model, and it still held this 94% re-identification. If we modify beyond that, of course, the result quality drops. So it's still quite robust somehow. Okay, so now I'm going to be more into systems and talk about the privacy-preserving traffic monitoring architectures that we have developed. So as I said in the introduction, we want to leverage the fact that most modern vehicles will be equipped with DSRC, so dedicated short-range communication systems. And these systems will somehow be useful to send data from cars in the form of sensing data to infrastructures to generate traffic maps. So the main advantages of using DSRC is that this is very cheap sensing. The cost is shared among users. Whenever you buy a car, you're going to have a DSRC system in it. So, in fact, as an operator of the infrastructure, you don't see all this cost. The main issue is, of course, the convenience for the user. So you have to have a system that is completely transparent. You don't want to have a system that requires the user to do many operations before generating data. It has to start very easily. But the problem with sending data out is that a fraction of the population doesn't like to have their privacy invaded. So you want to build a system that is completely bulletproof on this standpoint. Otherwise, you won't adopt the system for all vehicles. So you will have a system that will be adopted based on participating users. But we know that not that many people are going to participate to this kind of experiments, unfortunately. So we want to have a system that is installed systematically. And this is in contrast with typical traffic monitoring architectures, which is here. For instance, this is the architecture of Mobile Millennium. So you are using velocity and positional data. You're sending this data through an anonymization server, so you'll try to anonymize this data. And then this data goes to a centralized input database. It is combined with other feeds. You get estimations. Estimation, which means traffic maps, essentially. These traffic maps are fed back to the users. So here you address the privacy problem by stripping information from the users, but we know that even anonymous tracks can be somehow re-identified. So it's not quite completely bulletproof on the privacy standpoint. What we want to do in contrast is having a system that does all the computations locally. So it takes local velocity data, it takes local sensing data. All this data goes to a coordinator node, and you have a coordinator node per cluster. The operations of traffic estimation are done locally, so you get locally a traffic map, and this local traffic map is now forwarded to a centralized database and forwarded then to the users. So with this system, you have by construction that the information of the users stays local. You use distributed computing to solve the primes. And the vision for us would be to have a bunch of DSRC systems, so a bunch of cars equipped with radio communications. We would add to this, of course, a wireless sensor network that would consist in traffic sensors and in computational platforms that would perform the distributed computing operations. And then you would generate locally traffic maps. So you would generate these maps. These maps would be sent out to servers, but what is important is that these maps wouldn't contain the information on how they were generated, because that would be in the maps themselves. So I have to give just a bit of warning here. We are going to have a network that is segmented, as I said, in clusters. So you're going to break everything into clusters. These clusters can be time varying. Within each cluster, the information is freely exchanged among nodes, but the only information that flows between clusters are computed traffic maps. So which means that if you are in this cluster, you cannot have any information about what is exchanged there. So you won't know how many cars were there and how the data was generated. So of course, because we are sending traffic maps between clusters, that doesn't mean that we are not sending information about cars, because we have to anonymize the traffic maps. Traffic maps could still reveal something about users. For instance, if you have no vehicle in a location, and then suddenly you see your traffic map changing following the path of some probe car, you would assume that, of course, there is a vehicle there. So we have to do some anonymization. There are a bunch of strategies available, such as k-anonymization, which is adding a little bit of noise to your estimate, an optimal amount of noise to make sure that you can confuse at least k cars or k vehicles. So the implementation would be based on the parallelization of MILPs. So you would have a MILP, we would break it using branch and bound, and you would solve this over the wireless network. And to solve this MILP, we had to develop a new computational platform that was a bit more powerful than the currently available systems at the time where we worked. I guess now we have this kind of platforms that hit the market. But we wanted to have a system that is more powerful. So here it's based on the Cortex M4 processor. And this mode has actually built in a lot of features for energy optimization, for solar power. For instance, it has MPPT circuitry, so it can optimize the flow of solar energy. So these modes cost about $150 per unit, and we have estimated that on toy problems generated by a microsimulator, we would take about 2 or 3 seconds to solve a typical problem by one node. So in fact, we would be real-time by a good margin. Typically, traffic data doesn't come at this scale, so it comes at the scale of tens of seconds or minutes. So we would be clearly real-time. Now we have estimated the cost of deploying these nodes at about $2,000 per square kilometer in average. So this is some cost, but you have to factor out, when you want to compare this system with other systems, you have to factor the cost of 3G connections, for instance, in typical systems that use GPS plus 3G. Now I'd like to finish my talk on the traffic and flash flood wireless sensor network system that we have developed for cities. So this is a picture of the sensor that we have developed here. We wanted to have, as I said, a dual sensor system that could monitor both phenomena, traffic and flash floods. So you have actually here two components in this sensor. You have infrared sensor arrays that are measuring temperatures. So the nice thing is that these infrared sensors can measure the distance, the temperature in the field of view, as well as the local temperature around them. And you also have ultrasonic rangefinders that measure the distance to the ground. So this is to measure the presence of water, essentially. So traffic is monitored using these temperature anomalies from the PIR sensor arrays. They are also monitored by the ultrasonic sensor that is overhead over one lane. The street water level is estimating using the infrared, the ultrasonic sensor, but corrected with the infrared sensor. I will talk about this in a minute. On top of that, we can estimate water presence using the temperature anomalies. So we have done this on one example. I don't show it here because we have it working on one example, but rain doesn't open very often in Saudi Arabia, so we probably have to wait 6 more months before getting another data set. And on top of that, we can also estimate the rain rate using the reflections of the raindrops in the secondary lobes of the ultrasonic rangefinder. So really this sensor can measure a bunch of things, and we try to have as little sensors as possible, but exploit all data that was coming through these sensors. So this is the raw data from these infrared sensors here that allow you to monitor the presence of cars using the temperature anomalies. You can also monitor the presence of cars here using the ultrasonic rangefinder. So you can see, for instance, that these are always cars that have the same height. So they are, in fact, these are buses that go through the sensor at regular intervals. So we can actually estimate vehicle type, speed, and flow. So for the traffic estimation, this is really preliminary, but we are processing the data using wavelet transforms in order to get robustly the scale of the data and to get also the time of arrival of the data. So this allows us to simultaneously estimate the type of vehicle as well as the speed. And we have relatively good results on the estimation of speed. We have about 5 mph of error in typical speeds. And we have 90% good classification, I think, on the last results. So now I wanted to talk more about the flash flood estimation problem. So it looks very easy from a distance. Okay, you have an ultrasonic rangefinder. This is going to measure the distance between the sensor and the ground. So these sensors are pretty accurate. They have 1 centimeter of accuracy. So now that's a no-brainer. You just put this sensor and that's it. You're done. Well, if you look at the raw data, it doesn't work quite as well, unfortunately. And you will see that instead of measuring a constant distance to the ground, the sensor measures a distance that is time varying. So we were not surprised about this, of course. We built the sensor with that in mind. But we knew that temperature would play a major role here. Typically, for robotics application, we don't care about temperature compensation because we don't care about a few centimeters of error at 5 meters. It doesn't matter. However, for measuring the water levels at 5 meters, we care about a few centimeters of error because if you have 10 centimeters of error, you are completely wrong. And some floods actually happen with a few centimeters of water only. So you have to be much more accurate. So in order to be actually accurate here, we used, again, artificial neural networks. So we use supervised learning, and here this is very easy because you know that typically you don't have floods. You know when you have floods. So all the data that comes should be from data associated with a constant distance. So you put that into the supervised learning framework, and you force the system to recognize how to compensate for the temperature variations in order to have a good accuracy. And the measurement accuracy on the validation dataset is quite good. It's about 2 centimeters of error, of absolute error. And a bunch of this error is actually caused by spikes in the sensor readings, which are probably due to a problem of the power supply related to the mode. So we're going to try to fix this, but this is still good enough performance for as far as the water level estimation problem is concerned. And we even have validated this on a small flash flood happening in Omalkura University. So we have deployed 4 of these sensors on KAUST plus 2 in Omalkura University, these flash flood sensors. And you can see here that water levels spike actually at some point. So here it was just before midnight on the 9th of May. Both sensors registered a spike on their readings of about 7 to 9 centimeters. And you can see that actually a flood occurred. I mean, we asked people then later on. A flood occurred. The issue is that we lost our connection right after the flood. This is probably due to a reset in the computer. So they probably have shut down the power right after the flood. So unfortunately, again, when you are doing experiments, it always happens. But here, the 9th of May was actually a Friday, which is the equivalent of Saturday nights in the US. So nobody was watching what was happening on the sensor side. Okay, so this is for the fixed sensing component of the system. Now I'm just going to give you a few words on what we want to do for the mobile components. So as I said, we can use GPS data for the sensing. We can use a GPS Lagrangian sensors. We wanted to investigate now how IMUs, so inertial measurement units, would perform for this task. So we have done this experiment recently at Austin comparing a GPS and IMU system using the commercially available ArduPilot framework. And you can see that this is the speed estimates predicted by the IMU and the GPS, and they are quite good actually. IMU speed estimates, which are again obtained by integration. Over a few minutes, they don't drift significantly, and you can actually use that as traffic data. We want to use IMUs because they are more cost-effective than GPS. They also enable other monitoring applications, for instance, monitoring potholes or road condition. And also, they are completely insensitive to the problems arising to GPS in cities, which are multipath effects and the problems in positioning. In terms of flash floods, we have also built Lagrangian flash flood sensors. So these micro pingers here with 3D printed housing are prototype microsensors that we use both for this application, for this fixed flash flood sensing system. We can drop this flash flood on demand whenever you detect a flood, and track their location to detect where water is moving and to improve the quality of the forecast. We have also built, so that was my colleague Atif Shamim at KAUST, a new type of sensor based on printed circuits on paper, which is even cheaper. You can actually print it on wall-to-roll printing machines, and that's a good way of manufacturing sensors here. Now, I just want to conclude this talk. So here I presented one of the components of our research on wireless sensor networks. What we want to do now is solve more operational issues, for instance, in particular, developing schemes for optimizing the energy in the wireless sensor networks, because we're having solar-powered sensor networks, and it's very important to conserve these. So this is an experiment run by one of my students with multiple modes, and simulating energy harvesting and optimizing actually the power of the system over some finite horizon. We want also to develop low-cost IMUs. This is a prototype. This is just the circuit board design that we have thought of for IMU magnetometer system that could be plugged to any car and that could generate traffic data. So we want to investigate how this performs in conjunction with the fixed sensor network. And this UAV is actually from the KAUST department, so it's the Saudi Department of Aerospace. And it was lent to us for performing flash flood sensing experiments using these microsensors that I talked about. So this is a huge component of my research, but I haven't talked about this today. Feel free to ask any question if interested. So I want to acknowledge my group here with my PhD students and my MS students working hard. So it seems that my student is doing actually explain experiments. He's not actually playing, he's working on actually estimating angle of attack, side slips, and airspeed using hardware in the loop with our UAV system. So this is the picture of our UAV in flight, and I'm free to answer any questions you may have.
We have time for a couple of questions. I also want to say Chris will give a second seminar on Friday at 4 o'clock in the transportation seminar in Hearst Mining Building, 4 o'clock, and it will be on some algorithmic aspects that are behind this work. So I'm going to pass the mic for a couple of questions.
Hi, Andy from Mechanical Engineering. This is a high-level question. About this distributed computing, you can, the privacy issue. But since, as you mentioned, that the reason you want the traffic network is that you want to forecast the traffic in advance, right? Mm-hmm. So by not getting this, tracking each individual mode, does that undermine your forecast capability in the future?
So, if I understand your question, you mean do having a privacy-aware system, does it reduce the quality of our estimates or reduce the quality of the forecast of traffic, right? Well, with this architecture, on typical architectures, this is what you would do. This is a trade-off that you would do to address privacy. You would, for instance, lower the quality of your incoming traffic data on purpose to obfuscate the data, and of course you would get less accurate estimates in return. But with this architecture, we don't have to do anything of this, because in this architecture, all the data comes through the local nodes for computations, and this data remains local. This is really how the privacy preserving feature works here. You are privacy preserving simply because you are not exchanging this data beyond the cluster. So in other words, your quality of traffic estimate is not affected by the fact that you are having a privacy-aware system.
Second question is that since my research is in solar, and the last picture shows that you're doing something for the solar panel, can you just talk a little bit more about what's the work there?
Sure, yeah. So for the solar panel, I mean, this is a very good question, and this is related actually completely with our work in flash flood sensing. What we want to solve is actually the problem of maximizing the robustness of the network over some time horizon. Because this sensor network is a dual flash flood and traffic sensing system. You know that, okay, traffic is important, but the highest priority is in flash floods. You want to have the sensor up and running in flash floods. It doesn't happen very often, and that would be catastrophic if the sensor is not working there. Because it's solar powered, you have now a trade-off. Are you going to sense a lot of traffic and then be on the risk of running out of juice when the flash flood hits? That's really the issue. So we have built a game theoretic framework that allows you to estimate over a finite horizon how to arrange the sensing, the computation, and the communications in such a way that you maximize over that time horizon the minimum energy of the network. So that really maximizes the robustness of the system at some finite horizon. This is we already have some results. I haven't shown them here, but I'm happy to talk about this later.
So this is interesting work, but in California, can you create sensors that show that we have leaks of pipes and things like that could help alleviate the drought? Because you're 80% of the way there, and then you can just adapt newer technologies, use the infrastructure for something else, and then you can leverage both. And I think there would be a lot of opportunity for you.
Sure. Thanks. Yeah, I don't have specific ideas in mind related to pipeline monitoring. I think that would be a completely different problem in perspective. I mean, these microsensors could work, but the problem is that they would be affected probably by the signals. Their signals would not propagate beyond the pipelines. I guess you have.
Or you can use them as conductor. I mean, there's a lot, but you build the main thing is you're building the infrastructure.
Yep. Well,
just an idea.
Sure, and I mean, in terms of these microsensors that I talked about, like these sensors here, we are working right now on the next generation, which is sensors on steroids, with, for instance, additional sensing capabilities. We want to sense salinity, temperature, a bunch of things, but still keeping the cost extremely low. So keeping typically less than $1 or $2 per sensors for dedicated applications. For instance, if a river is polluted or something, you could throw these sensors, and that would be disposable. You wouldn't recover them, but because it's so cheap, it wouldn't matter.
Yeah, I have a question. Seems like every year, I mean, there's an annual flash flood in China and Southeast Asia. Are they making the newer cars more high-tech and that it can resist moisture in the engine train so the car doesn't die?
Yeah, so that's the biggest problem associated with flash floods. It's really a catastrophic event that doesn't look so terrible when you look at it in pictures, but you have to know that even SUVs can be carried away by floods with only 60 centimeters of water. Actually, that's enough to bring a SUV down. People can drown with less than 20 centimeters of water. I think this has been documented. So it's really very, very, I mean, it's extremely dangerous, basically, but it doesn't look very dangerous. But I think the technology is still far away from helping people there. And the main issue that we had in Jeddah was really the lack of information. I mean, during the 2009 flash floods, most of the people that drowned were in highway underpasses, and these highway underpasses filled very quickly. There was no information at the time. It was not even raining over the city. So the rains occurred on the mountains 50 kilometers away. And because there is no warning system, actually, 400 people died, but that could have been completely avoidable if a warning system was in place. An accurate warning system, of course. We don't want blanket statements. We don't want to send an alert every month for something that should happen every 100 years. But people have to know when it's an exceptional severity flash flood, they have to know what's happening and where it's going and who are concerned and how to deploy your emergency services.
So you mentioned that you can track vehicles over roughly 10 re-identification steps. Do you have a sense of the physical and temporal scale of that tracking?
Yes, so here on the applications that I showed, the scale was a few kilometers. So I would say 5 to 10 kilometers approximately, the scalar free identification. And this is only with this framework. Maybe if we combine this again with other features, and we haven't thought of every feature available, but essentially the framework helps you to give you additional features to train the neural network. And what is nice is that these results were re-obtained on validation dataset. I mean, if you train things, of course, the more parameters you add, the better it is. But on validation, it's hard to validate something with additional performance, because most of the time you add features that are useless for classification.
Thank you.
Right. So please join me in thanking the speaker again. And again, if you're interested, there's a second talk on Friday at 4 o'clock in 290 Hearst Mining Building. Thank you.
Thanks.